Hello and welcome. This is Cambridge O-Level Physics Paper 4, alternate to practical. The subject code is 5054. This is October-November 2021 exam. This is the variant 1 of this paper. Let's start. First question. A student investigates how the period of a pendulum depends upon its length. The diagram is shown here. So we have a clamp and a plumb line, and a pendulum bob is attached to a support, and there is the length of the pendulum bob from the center of the pendulum to the point on the support is denoted by letter L. It says the student arranges the apparatus as shown, clamps the string of the pendulum in this position. The length of the pendulum is the distance from the center of the pendulum to the point on the support. So first part, it says measure the distance L on figure 1.1 to the nearest millimeter, record your answer or result. So how to do it? So first of all, you have to have a ruler with you. You need a ruler and you have to use that ruler to measure this length. Ruler and measure this length using that ruler, and when I have measured it on my question paper, it comes out to be something around 5.1 something, and according to your you can say the marking scheme, they have the length around 5.2 centimeter, and generally your marking scheme says that plus minus 0.1 will be a good answer. So 5.1 or 5.2 is a good choice. So I will go with this value according to your marking scheme. So the length, when we measure it using a ruler, it comes out to be 5.2 centimeter. Part 2, it says figure 11.1 is drawn to scale of 1/8 of the full size. Determine the actual length, that is capital L, of the pendulum from the point of the support to the center of the pendulum bob. So this is 1/8 of the total length. So total length is actually 1/8 times of L. So total length will become 8 times L, and it is 8 multiplied by, we have used 5.2 according to our marking scheme. So it comes out to be 41.6 centimeters. So the length over here is 41.6 centimeters. Okay. Next part, part B, it says the pendulum, sorry, the period is the time taken for one complete oscillation of the pendulum. One complete oscillation is one complete swing. For example, from the middle to one side, through the middle to the other side, and back to the middle. It says number one, the student adjusts the length of the thread until length capital L is 15 centimeter, gives the bob a small sideways displacement and releases it so that it oscillates, records the time for 10 complete oscillations, repeats the procedure 2 more times. The following values of the time for 10 complete oscillations are recorded. So the values are 7.4, 7.8, and 7.7 seconds. Calculate time to 10 seconds, T10, the average of the time for 10 oscillation, give your values to two significant figures. Okay, so how to calculate the average? So you have, remember, you have to show the working over here properly. Do not just simply use calculator and write the value. So this is for 2 points. 1 point is for the showing the working properly and then writing the correct answer to two significant figures. So if you're going to write out the answer directly, you will lose points. So T10 is basically 7.4 plus 7.8 plus 7.7 divided by 3. So that will be our average. So T10 comes out to be 7.6333 and so on seconds. And for two significant figures, remember the answer will be 7.6 seconds. So my answer will be 7.6 seconds. So first significant figure is this, second is this. Okay, but if they have asked us to give it to two decimal places, so answer will be 7.63 seconds. This is for two decimal places, not significant places. So this is a mistake some of the students make while writing down the values. They confuse two significant figures with two decimal places and they lose points in this case. So please do not make this mistake in your exam. Next part. Part 2, it says the student repeats the procedure in B1 for the length 20, 25, and 30 centimeters. Sorry, 20, 25, 30, and 35 centimeters. The results are shown in the table 1.1. So the table below shows the results for the what the student has calculated. So so for 15, the results for 15 are these or this what he has calculated. So it says complete the table using the values from using the answer from B1. You need to calculate T and T square. So we have the T10 value as 7.6. T in seconds is T10 divided by 10. This is 0.76 seconds. So this becomes 0.76 seconds again, and T square just use the square values. So 0.76 square, and it's always, and these values are up to 2 decimal places, so round off your results to 2 decimal places. So if I round off my result to 2 decimal places, it comes out to be 5.58, and that goes with how these values are used or being observed in the table or being jotted down in the table. So then part 3 it comes. So this is how we complete the table. Part 3, it says explain why the student measures the time for 10 complete oscillation rather than for one complete oscillation. So generally, what happens here is that that we are using a stopwatch to calculate the time, and if we are going to make one oscillation, there is a human error, or there is a human reaction time to when you switch on and switch off the stopwatch. So there is a good significant amount. Also, for example, one oscillation is 1 second, and their human reaction time is 0.5 seconds. So the error is 50%. But say, for example, if you're measuring up to 10 seconds, uh, your value or your say the number of seconds for 10 oscillations is 10, and again reaction time remains the same, it's 0.5. So the error in the measurement is around 5%. So what happens here is that the more you increase the number of oscillations to measure the time, the effect of human reaction error on the overall reading, which especially comes out very high when we have one oscillation, becomes very small, and that basically helps us getting a much better and accurate result. So this is how we have, or this is the main key reason for that. So just why the students do. So this reduces the effect of human reaction error on the measurement of time using a stopwatch. Um, and therefore more accurate result can be obtained by measuring time for large number of oscillations. So another way of writing it is to use the words such as the percentage of react, or the percentage of error reduces if we use more number of oscillation, or if we measure time for more number of oscillation rather than one complete oscillation. This is another way of writing it, or saying something like that. So then part 4, it says on the grid shown in figure 1.2, plot the graph of t square. So we have to use this on the y-axis. This is on the y-axis, and L, and that is the length on the x-axis. Start your axis from 0, 0, draw a straight line of best fit. Okay, so this is how a graph is given to us in this exam or in this paper. So I'll try my best to show how to draw this thing. So remember, good practice is to use more than 3/4 of the graph available. Okay, so it's good practice to use more than 3 of graph available. And number 2, for best fit straight line, it's good to have points equally distributed across the line. So if you have 1 point going above the line, make sure that there is at least 1 point that goes below the line as well. So okay, so on x-axis, first of all, label it x-axis. This is my x-axis. This is this is my y-axis. So on the y-axis, what is the variable t? T is measured in second square. On the x-axis, what we are using, length, that is in centimeters. So again, I'll start with 0. So 5, 10, 15, 20, 25, 30, 35. So we are good. So take it as 5, 10, 15, 20, 25, 30, 35. Now on the y-axis, 1, 2, 3, 4, 5, 6, 7. So now on the y-axis, so if we are going to see, so if you are going to vary the time, it is somewhere from 0 to approximately 1.4. So let's see. So if we are going to go and give 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, and this is 1.4. So we are have a good distribution of all the values over here. So now let's try to see where exactly we are having the plot. So for 15, we have 0.58. So 0.5 is 15 is here on the x-axis, on the y-axis 0.58. So 0.58 is somewhere here. Oh, so 0.58 is somewhere here. Again, I draw it something like this. So this is 0.58. Then on 20, we are having around 0.79. Oh, sorry, 0.58 is somewhere here. So 0.5 here is somewhere here. Sorry, this is not 0.58. On 20, we have 0.79. So 0.79 is, this is 0.78. This is somewhere between 0.78 and 0.79. This is 0.79. Then on 25, we have 0.98. So 0.98 is over here. This is 25. Then 30, we have 1.17. 30, this is 1.1, 2, 4, 6, somewhere here. So we have somewhere 1, 2, 4, 6, somewhere here. We have 0.17, and then on 35 we have 0.39. So it goes somewhere here, somewhere here. Okay, so that is sort of an end of my screen. That is okay. So let's so when you are going to draw this line, so make sure you and draw a best fit straight line. So I'm trying with whatever the tools I have to see that what sort of line we have. So yes, there will be some points on the line. There will be a couple of points that are not on the line, but it would be overall fine. Okay, so so extend it a little back, and you can use 2 dotted lines to show as well, or even if you can start from 0, 0 as well, that is also fine. So Moving ahead, it says determine the gradient g of your line, show your working, and indicate on the graph the values you use. So again, this is of 2 points, so we have to show our working. So part 3, gradient. So gradient, for gradient, remember uh, g is change in y by change in x. So change in y, so first of all we have to select 2 points, and those 2 points are not the ones that are given. So on your line, select 2 points. Say somewhere you select this point, and I call this as A. On the x-axis, this point is say 17.5, and on the y-axis, this is say zero point 0.7. So on the y-axis, this is 0.7. Okay, and then I select some point somewhere here. Okay, so somewhere here, on the x-axis, it comes out to be say x-axis 32.5, and on the y-axis it comes out to be 1.29, 1.3. So I'm say 1.3, you may call it. So it's up to you how you use it. So okay, so I label it A, label it as B. So go down on B, something like this, and go down something like this. So this is your point C. So if this length, so on change in Y, BC divided by AC. So that length, or you just simply find the slope of this graph, and that slope is delta Y is 1.3 minus zero point 0.7 divided by 32.5 minus 17.5, and the value comes out to be something, I think it would be around 1.4, 0.39 something. So let me use the calculator to see how it comes. So it comes out to be 1.3 minus 0.7, 0.6, and it is divided by 17.5. So it is exactly 0.04. Okay, so it is exactly 0.04, and the units are second square per plus centimeter. Okay, so this is my slope. So on the next graph, show you, if I'm going to show my working, so you can show your working over here and over there as well. So 13.7 minus 0.7 divided by 32.5 minus 17.5, and this comes out to be 0.04 second square divided by centimeter. So my gradient becomes 0.04 seconds square divided by centimeter, and that is my answer for this case. Okay, the next part, it says theory suggests that gravitational field strength G is equal to 0.39 divided by G. Use this equation and your value in part B5 to calculate the value of G. So we calculated it around 0.39 and we divided by 0.04. So it comes out to be something around 9.75. You can say newtons per kg, the value of G. And this value of G is 9.75 newtons per kg. Okay, so how you compare the value of G, and accepted value is 10. So our value, so percentage error, if I'm going to say, it is approximately equals to 10. And so say, remember your what your marking scheme says. So marking scheme says that this value of G is something, oh sorry, the value of capital G. Capital G is something, if you're using your graphs, it's 0.039 to 0.041. If you calculate something between this these values using your graph, it means that you have developed a good graph and you'll be getting complete credit. But if your value from the graph or from the best fit straight line and the method I have shown you earlier, it doesn't fall in this category, then make sure that you correct your mistakes, because in that case you will be losing points in your exam. So again, in this case, if I'm going to say calculate the percentage error in this case, this is say 10 minus 9.75 divided by 10 into 100. So my percentage error will be 0.25 divided by 10 into 100. So it comes out to be 2.5%. So this is well um, percent. So error is much less than 10%, plus minus 10%. So my error is much less than that. So we are good, and we can say that state whether the two values agree with each other and justify your answer. So yes, the values agree with each other. As the percentage error is 2.5%, which is below acceptable range of plus minus 10%, acceptable error range of plus minus 10%. You can say that generally, or in a very good experiment, this range is plus minus 5%. But again, experiment to experiment, it will vary. But your marking scheme says that if your results are within the 10% range, you can say that your results are fine. So we can easily say that these two values are comparable, because they are much less than 10% of the acceptable range of error. So we can say that the value is accurate enough. Okay, so next question, next part. So it says, it is question number 2. It says a student carries out an investigation to find the specific heat capacity of copper, and specific heat capacity C of copper. The student places a small block of copper on a balance to find mass M, as shown in figure 2.1. So the mass is M. So record the mass of the block and correct to 1 decimal place. So remember, this value is given to 3 decimal places. So correct to 1 decimal place. So 1 decimal place will be 29.165. So first of all, 29.17 it becomes, and then we can say 29.2. So my actual answer, or correct to 1 decimal place, is 29.2. So remember why. So if this value is equal to or more than half, add 1 to this number, so it's just 7. And if we are here at 1, if this value is more than 5, add 1 to this number, or sorry, so if this y is equal to or more than 5, add 1 to this. And then again, on in part B, if if this is 7 is more than 5, so add 1 to this number. So 1 plus 1, 2. So this is how we do it, or do the approximation in our case. Then part B, the student measures the volume of water in a measuring cylinder as shown in figure 2.2. Record the volume of water in figure 2.2. So this is my reading. So remember, we have to measure the lower meniscus, and in case of mercury, if it's there, so we have to measure the upper meniscus, because so water for lower meniscus. So lower meniscus is 1, 2, 3, 4, 5, and 46. One above, so it is 46 centimeter cube. Okay, so for mercury, remember, you always have to measure the upper meniscus, and for water, you have to measure the lower meniscus. Next part C. The student, it says, pours the water from measuring cylinder into a beaker, records the initial temperature of water as 23 degrees centigrade, places the copper block in the boiling water for several minutes until the block is at temperature of 100 degrees centigrade. Then he lowers the copper block into the beaker of water and stirs the water until reading on the thermometer stops rising. Records the final temperature of water, which is 27 degrees centigrade. The specific heat capacity C of copper can be found using this equation. Okay, use your results in A and B. So in A, my results in A, the mass was remember 29.2 grams. B was my volume was 46 centimeter cube. Um, and and the value of theta 1. So theta 1 value is 23 degrees centigrade. To calculate the value of C, so let's see what we get. So we get C 46 multiplied by 4.2 multiplied by 27 minus 23 divided by mass is 29.2 uh, multiplied by 100 minus 27. And my results comes out to be 0.3625. And this is my results. So my value of C comes out to be 0.3625. And remember the units of C, specific heat capacity, it is joules per uh, grams per centigrade or joules per kilogram per degree centigrade. Either one of this is fine. So your marking scheme goes with this. So you can go with this. Generally, if I have to write it, I would go with joules per kg per degree centigrade. This is what my preference would be. But anyways, I will go with the marking scheme because these are actually the SI units or the way in which the units are written in terms of kg. But anyways, okay. So part D of this question, it says the method does not give the accurate value of C. Suggest one reason for this. So remember, there can be many reasons. So student is actually doing what? So generally, so it is he is taking out the copper from this is the heated copper block and placing it in water. Some of the energy may be lost to the atmosphere while he's moving copper block from one point to the other. And the second thing is that this block is placed in a beaker, and for that beaker, the temperature is measured. And the beaker is actually not properly insulated. There is no point of insulation is mentioned here. So there is some heat loss from the beaker. So if there is some heat loss from the beaker, then then this method at least will not give us the accurate value of specific heat capacity. So let's write this thing. So say one reason, uh, sum of the heat is lost to the ambient from the beaker, which results in inaccurate value of C, or we can say sum of the heat is lost during the movement of copper block from heating plate to the beaker of water. Okay, and this again results in inaccurate value of or inaccurate measurement or calculation of C. Okay, then next question. So question number 3, it says the student investigates the resistance of a thermistor. The student places the thermistor in a beaker of cold water, connects the thermistor as shown in figure 3.1. Part A, part number 1. On the figure 3.1, draw a voltmeter connected to measure the voltage across the thermistor. So remember, this is our thermistor and voltmeter. So voltmeter is always connected in parallel. So parallel to this thermistor, so the parallel will be something like this. So this is my voltmeter. So this is how you connect a voltmeter. So ammeter is in series. See, the ammeter is in series. So the voltmeter is always connected in parallel wherever you have to measure the voltage. So this is how it is connected. Okay, next part. Figure part A, part 2, it says figure 3.2 shows ammeter. So this is A, this is ammeter. Measures current. This is V, this is voltmeter, and voltmeter measures the voltage. Shows the ammeter and voltmeter readings when thermistor is in cold water. So remember, these readings are of cold water. So record the values of I and V. So for I, this is 0.3, this is 0.32, 0.34. Okay, so my first reading will be 0.34 amperes for current or ammeter. For the next part, my voltage reading will be 1.5, 1.6. So 1.6 volt will be my reading for this. Okay. Next part number B. The student adds some hot water to the beaker, stirs the water, repeats the reading of current and voltage. So in the beaker with this thermistor, the student further adds more water, pours more water, and if he adds more water or hot water into it, the temperature of this thing will rise. So the temperature of this thing will rise. It means that the resistance or thermistor is a temperature dependent resistor. So temperature dependent resistor, the temperature will rise, means that that the resistance will change. The resistance will change, the voltage and the current will change. Okay. So remember this thing. So explain why the student stirs the water. So what is the reason? So the stirring basically distributes the heat energy uniformly across water. And that is why student is doing, because thermistor is a temperature dependent device, and unless the whole water is at same temperature, the resistance will not be stable enough, and the voltmeter and ammeter will keep on switching until the thermistor settles to a specific value, or the temperature, and that settles, and the thermistor only settles till the temperature of the water is uniform, and or it's across uniform across the whole beaker. So you can say the stirring helps to achieve uniform distribution of temperature across so temperature uh, of water in the beaker helps achieve uniform distribution of temperature of water in the beaker. This results in a stable value of resistance offered by the thermistor, and thermistor, or you can say hence accurate results can be measured. Okay, and that is the only reason why it is done. Then part 2, it says the voltmeter reading doesn't change. So the voltmeter reading, remember the voltmeter reading was 1.6 volts. Okay, the new ammeter reading, so the new ammeter reading is shown over here. So new ammeter I dash, I can call it I dash. So I dash is 0.4, 0.5, 0.52, 0.54, 0.56. So the new ammeter reading is 0.56 ampere. And remember the previous I ammeter reading was 0.34. So it was 0.34 amperes. This one was the previous reading, and this is the new reading. So remember, resistance is given as uh, given by the equation E equals Y. So this is basically the Ohm's law. Ohm's law is given. State how the resistance of thermistor changes as the water becomes hotter. So remember, our thermistor is inversely proportional to temperature. So if your temperature increases, your resistance will decrease. Okay, and vice versa. So explain how the readings is changing. So just simply write it as the resistance of thermistor is inversely proportional to the temperature. The temperature of water rises, uh, resulting in decrease in resistance. And since if we can see this current, so if so V equals to IR, uh, and say I equals to V by R. So if my resistance will decrease, my value of current will increase for my voltage to remain constant. So what we have seen here from this equation is that, or from these measurements, is that my value of I has increased. So my value of I has increased and my voltage has remained constant. It means that my R has decreased. So we can also write it that temperature of water rises, resulting in decreased resistance. This can be seen from, or this can be observed, is a good word to use here. This can be observed from ammeter readings as the current changes from or not changes, current increases from 0.34 amperes to 0.56 amperes, comma, causing resistance to change from, or again, not change, resistance to uh, you can say what will happen to resistance. Okay, I will not write it, I will calculate it for you. So first of in case one, I equals to 0.34, V equals to 1.6. My resistance will be 1.6 divided by 0.34. So what is this value? Let's calculate it. So it is 1.6 divided by 0.34. So this value is around 4.705 ohms. So my next value, remember, for the next case, the current value is 0.56, my voltage is 1.6, and resistance value 1.6 divided by 0.56 oh, and my resistance comes out to be let me calculate it, 2.85. It is 2.857 ohms. So causes the resistance. So my resistance is, this is our initial and this is R dash. So resistance to decrease from 4.7 to 2.86 ohms. Okay, and this is how you write this answer. I mean, again, a good student will will use the readings or will explain this solution, this answer with the help of these calculations, and this is what the examiners will be looking for, that how good your concepts are and how good you able to understand this phenomena that is happening. The first line, the resistance of a thermistor is inversely proportional to temperature, is actually a property of thermistor. But what exactly they are trying to find out is that say if you do not remember what exactly a thermistor is, uh, so how you will be able to see what is happening over here using the uh, available information, and that is what you can, that is how you can do, or you can say that satisfy the examiner. Okay, so next part, question number 4. Question number 4, it says the figure 4.1 shows a cardboard lamina with 3 small holes, a piece of string with a small mass attached to one end. The string and mass together are called a plumb line. Okay. First of all, it says that describe an experiment that uses this apparatus as shown in figure 4.1 to find the center of mass of a lamina. A clamp, boss and stand, and a long pin are also available for use. Okay, so you must include a label diagram for your answer. So let me draw a label diagram here. So how you're going to use, so basically we'll use the clamp. So this is my clamp and this is the clamp holder, and you have the pin over here. This is my pin. You can say this is my clamp. Sorry, this is clamp. This is boss and stand. Okay, and this is pin. So what you can do is you can have your lamina something like this. This is say your whole let's call this whole B, let's call this whole A, this A, B, C. So I mean you can start with whole B. Say this is your whole B, somewhere is your whole A, and somewhere here is your whole C. So first of all, what you can do is you suspend it from this point, your lamina from this clamp, and add the plumb line here. Sorry, let me say draw this thing in a much better manner. So this is my whole A, this is my whole B, and suspend my plumb line from here. Okay, so this is how my plumb line looks like. This is plumb line. Okay, so this is how a plumb line looks like, and then you just simply draw a line for this. So we call it as figure A, and then you can also draw a figure B. You can draw a figure B, again something like this. This is your boss and stand, this is clamp, and this is pin, and this time you are suspending your lamina from point A Point A is here, B comes somewhere here, C comes somewhere here. Okay. Um, so with A, you will see that your plumb line will be like this. So, and again, draw the line on this. Uh, uh, I mean, from where the plumb line is going, and these two lines from B and A will intersect, and the point where these two lines intersect will be the point of center of mass. Okay, so now let's try to explain this part. So first of all, you basically suspend the lamina from a from hole B on the pin attached to the clamp and stand as shown in fig A. Okay, then suspend the plumb line from the same point. Okay, suspend the plumb line from the same point. Draw a line following the plumb line. So draw a line, I would say, on the lamina following the plumb line. That is a better way. Draw a line on the lamina, following the plumb line. Okay, following the plumb line. Repeat the procedure with holes marked A and C on the lamina. The point of intersection of the three lines will be the center of mass of the lamina. Okay, that is how you do this experiment. It's a pretty simple one. Again, so this is for 4 points. One will be for drawing a good diagram. Then they want you to say suspend this from hole, suspend the plumb line, draw a line, and fourth point is the point of intersection. So these all 4 points, and along with the diagrams, if you write it like that, you'll get complete credit for this answer. Okay, so so also you can show something like this: dotted line here, dotted line here, one dotted line here. So this is, you can say, center of mass, something like that, to make sure that when it is suspended, for the examiners, that yes, you know how to solve this question, or answer this question, and you know the concepts correctly. Okay, next part, it says suggest how the position of center of mass in found in A can be confirmed using a sharp pin only. Okay, so remember this is, for example, you have a sharp pin. Okay, this is a way big pin. So for example, this is um, uh, the tip of the pin. So you try to, you basically, the point you have found out, you try to balance. This is your lamina, this is pin. So if you try to balance this lamina over the tip of that pin, very small object, your lamina will perfectly balance. And that is one of the property of center of mass of any object. So just simply uh, write it as balance the lamina over the tip of the pin. Balance the lamina over the tip of the pin at the uh, position found in A if the lamina balances the position is the center of mass of the lamina. Okay, so this is how you write the answer for this question, and this is the last part of this paper. So thank you, I thank you all for listening, and I wish you best of luck for your exams. Thank you very much.